Dear students, so in our previous video, we have already covered our internal static indeterminacy of case 1, that is pin jointed plane frame for 2D truss. Now in this session, we will going to discuss our case 2, that is the 3D truss, that is pin jointed space frame. So in 3D truss, we know each member is having one internal force, that is axial force, but each joint has three conditions of equilibrium, that is summation of fx is equal to 0, summation of fy is equal to 0, and summation of fz is equal to 0. Therefore, total conditions of equilibrium at j number of joint will be 3j. Out of 3J equilibrium conditions, 6 conditions are used to find external support reactions. Hence, we are having dSi is equal to, this is dSi, not dSe, internal static indeterminacy is equal to total number of internal reactions minus available equations of equilibrium. So we are having total number of internal reactions are m and available equations of equilibrium are 3j minus 6. So this is your DSI, internal static indeterminacy will be calculated as m minus 3j minus 6, where m is the total number of members and j are the total number of joints. Okay, so this is our case 2, and move on to the next, that is case third, that is 2D and 3D rigid frames. Okay, so we know in rigid frames internal indeterminacy will not exist if it forms an open configuration like a tree. To check internal indeterminacy, following thumb rule may be applied. What is the thumb rule? So if a structure is internally determinate, then it is impossible to make a cut anywhere in the structure, splitting the structure into two free bodies. And the second condition is, in case of internally determinate structures, it is impossible to return back at same point without retracing the path. It means internally determinate structures do not have any cyclic loop. Okay, so we know in case of 2D and 3D rigid frames, if I'm talking about two-dimensional, that is 2D rigid frame, each member has three internal forces, that is your Rx, Ry, and Mz. And in 3D rigid frame, each member is having six internal forces, that is your Rx, Ry, Rz, and Mx, My, Mz. So it means each closed loop in 2D has three internal indeterminacy, and each closed loop in 3D has six internal indeterminacy. So hence we are having a formula for 2D rigid frames, that is DSI, that is internal static indeterminacy is equal to 3C, and DSI is equal to 6C for 3D rigid frames. So 3C is for 2D rigid frames and DSI is equal to 6C for 3D rigid frames. Okay, so this is the formula you have to keep in mind. Okay, and what is the C? C is your number of closed loops. Okay, so if I am having a closed loop 1, then C value is 1. Okay, and if I am having closed loop 2, then we are having a C value is 2. Okay, so you know, in above analysis, all the joints are considered rigid here. Okay. So if I am having a joints hybrid here, so if some of the joints are hybrid, that is your hinge joints, then what happens? Then the sum of the internal reactions will release. Okay. And your DSI value will be reduced. Okay. So internal static indeterminacy value will be reduced here. Okay, so you have to keep in mind this point, that this is the case when your all your joints are rigid, then DSI is equal to 3C for 2D rigid frames and DSI is equal to 6C for 3D rigid frames. Okay, and if we are having some joints are hybrid or hinged, then our internal reactions will release and DSI value will be reduced. So the DSI value will be 3C minus RR for 2D structures, and DSI is equal to 6C minus RR for 3D structures. Okay, so here your what is this RR? RR is the total number of internal reactions released. Okay, so you have to keep in mind. And what is this RR? Okay, so let's take one example here, how to calculate your RR value, number of internal reactions released. Okay, so if this is having a frame, this is your fixed support A, this is your fixed support B, and this is your member FG here, and DC here member, and CE, and C is your internal hinge. Okay, so at internal hinge, that is at point C, we know your moment value is 0. So moment at C is equal to 0. So here one internal reaction, one internal force, that is your moment at C, is released here. So we are having a RR value of 1. Okay, so you can calculate also your RR value as here at point C, that is your internal hinge. Two members are meeting here. Okay, one is BC and another is EC. So you have to calculate your RR value. So what you have to do, you have to keep in mind that to calculate your RR, you have to summation of m dash minus 1 is the formula to calculate your RR. So here, what is this m dash? M dash is the number of members meeting at the hybrid joint. So number of members meeting at hybrid joint are 2, that is BC here and EC here. So 2 minus 1 is your 1. So RR is equal to 1 here. But directly we know that at C point there will be only one internal force, that is moment at C is released. So RR is equal to 1 here. And okay, so by this way you can calculate the RR value. So if you are having an internal roller, then this is D point. At internal roller, we know at this D point your two internal forces are released. One is your axial force and another is your bending moment. So RR value here are 2, that is for axial force and for bending moment. Okay, so you can see this example also. This is your roller. Okay, so at this point, E point, this is your E point. At this point, shear force is released here. So here RR value is only 1. Okay, so you have to keep in mind your internal hinge, internal roller, and internal supports. And now the number of release forces RR depends upon the number of members meeting at the hybrid joints. Okay, so number of released forces, that is your RR value, depends upon the number of members meeting at the hybrid joint. Okay, so whatever the members meet at hybrid joint, there will be the value of RR. Okay, so this is your RR. Then RR is calculated as number of members meeting. That is 1 here, 2 here. 2 minus 1 is 1. So your RR value is 1 here. Okay, so you have to keep in mind this clause also. If you are having a frame like this, that this is your fixed support at A, this is your fixed support at B here, and this is your internal hinge at C and internal hinge at D here. Okay, so to calculate your RR value, number of release reaction, if we are seeing here this point C, number of members meeting here are is this one and this is 2. So formula we are having RR is equal to summation of m dash minus 1. M dash is your members. Number of members meeting at this hybrid joint is 1 and 2. So 2 minus 1 is 1. So RR is equal to 1 at point C. And for point D, here we are having a members meeting at this internal hinge D is 1 here, 2 here is, and 3 here this. So summation of m dash minus 1. So 3 minus 1 is 2. So at D, we are having a RR value of 2 and at C RR value of 1. So total RR value is 3, that is 2 plus 1. So RR is equal to 2 for at point D and RR is equal to 1 for point C. So we are having a number of released reactions is equal to 1 plus 2 is equal to 3. Okay. So we can generalize internal reactions released as per follows. That is for plane structures, RR is equal to summation of m dash minus 1 for 2D frame, and RR is equal to summation of 3 times of m dash minus 1 for space frame. Okay. What is this m dash? this is important. M dash is the number of members meeting at the hybrid joint. Okay, so M dash is important. So to calculate your RR, M dash value you know. Okay, so hence DSI can be written as, that is your internal static indeterminacy, will be calculated as your 3c minus summation of M dash minus 1. Okay, so 3c minus summation of M dash minus 1 is your RR value for 2D, and DSI is equal to 6c minus RR, that is your 3 times of M dash minus 1. Okay, for 3D. So by this way you can calculate your uh, DSI value. Okay, so where, what is the C? C is the number of closed loops, and what is this M dash is? M dash is equal to number of members meeting at hybrid joints. Okay, so M dash is equal to number of members meeting at hybrid joint. Okay, so overall degree of static indeterminacy, that is your DS, will be calculated as external static indeterminacy plus internal static indeterminacy. Okay, we know in our previous video we have already covered our external static indeterminacy, and we have already covered this part in this video only, internal static indeterminacy. So by adding external and internal, we are having a overall degree of static indeterminacy. Okay, so we are having our alternative approach to find your DS value. So you can see here, to calculate your static indeterminacy for plane truss, that is 2D truss, DS is equal to total unknown forces, that is your external force plus internal force minus total equations of equilibrium available we have. So we are having internal reactions, that is your M here, number of members, that is number of internal reactions M, and we are having your external reactions as RE here. So and we are having a J is equal to number of joints. So M plus RE is your external plus internal forces, and minus we are having for 2D 2 times of number of joints. So total equations of equilibrium available is 2J. So we are having a formula for plane truss, 2D truss, ds is equal to m plus re minus 2J. Okay. So if ds is equal to 0, then truss is statically determinate. If greater than 0, then truss is statically indeterminate. And if ds is less than 0, then truss is statically unstable. Okay. So for greater than 0, we are having a statically indeterminate truss. For less than 0, it is unstable. So for space frame, that is your 3D space frame, ds is equal to m plus re minus 3j. The only difference is your 3j. In 2D truss, we are having a 2j, okay, and for 3D truss, we are having a 3j. Okay, so m plus r is your internal and external forces. Okay, and 3j is your total equations of equilibrium available. Okay, you have to keep in mind. And for your 2D rigid frames, we are having a formula ds is equal to 3m plus re minus 3j. Okay, so 3m plus re minus 3j is your formula when all the joints are rigid. If we are having some joints as hybrid, then ds value is 3m plus re minus 3j minus rr. Okay, so your released reactions will also calculated when you are having some joints as hybrid. Okay, so ds value will be calculated as 3m plus re minus 3j minus rr. Okay, for 2D rigid frames. And for 3D rigid frames, we are having a formula 6m plus re minus 6j when all the joints are rigid. And if we are having some joints are hybrid, then 6m plus re minus 6j minus rr. Then number of released reactions we also encountered. Then static indeterminacy will be reduced. Okay, so these are some important formulas to calculate your internal static indeterminacy for your pin jointed space frame truss, that is 3D truss, that is for 2D rigid frames and for 3D rigid frames. Okay, so these are some important formulas, and based on these formulas, we will cover our numerical parts, and which is usually asked in your exams, the questions. Okay, the numerical important questions. So this is I will sum up. Okay, so here your case 2, this is your 3D truss pin jointed space frame. So DSI, so this is a DSI, not DSE, this is a DSI equal to, that is your internal static indeterminacy, m minus 3j minus 6. Okay, so not your external static indeterminacy. So dsi is equal to m minus 3j minus 6. Okay, hope it is clear. And case 3, for 2D and 3D rigid frames, we are having a formula dsi is equal to 3c for 2D rigid frames, and dsi is equal to 6c for 3D rigid frames, and c is equal to number of closed loops. And dsi is equal to 3c minus rr for 2D if we are having hybrid joints also, and 6c minus rr for 3D structures. Okay, so this is how we calculate our static indeterminacy, internal static indeterminacy, and overall static indeterminacy. Okay, so overall static indeterminacy will be your external static indeterminacy plus internal static indeterminacy. Okay, so let's close this session, and thank you so much.